Hello. Hi everyone. First of all, Happy New Year. It's the first edition of 2025 Space Cafe Tokyo. And my name is Tilina. I'm from Earth Life Science Institute. Welcome to January edition. So we have a special speaker this month, Sudha Rajamani. She's a professor from, let me actually read the institution's name because we always say Iceland, but sometimes I can't remember the actual name. So it's the Institute of Science, Education and Research, ISA in Pune. And Sudha's working on astrobiology. So today she's going to tell us about how life came about in our planet, but big picture kind of overview. And Sudha's not a stranger for Japan. This is the 5th visit. So if you are new to Japan, actually you can ask for tips from Sudha. And so currently Sudha is visiting our institute as a part of joining our symposium annual conference, which was last week, and also for a lot of collaborations, and staying for another 1.5 weeks in Japan. And so since it's a 5th visit to Japan, you can imagine outside of work, also one of her hobbies is a lot of traveling. So if you're interested in discussing about travel outside of asking questions like how did we come about, you can also talk about traveling. So yeah, let's kick off today's event with Sudha. Thank you.
I'm giving a outreach talk in a setting like this. The only other time I did this was in a bar in India. Yeah, was in a bar in India, and I thoroughly enjoyed that experience because it generally sees a very diverse set of audience, some of whom have a little bit of background in science, and most of whom who just love science for the craziness that it encompasses and whatever we have to learn from the various sort of areas of sciences. So I stumbled into this field completely by chance a couple of decades ago. I fell in love with it and I never looked back, and I decided I will start my group in this area of astrobiology. So today I'm going to give you a flavor of how do we think in the field about how life might have originated on our planet. And I think a good number of you would have heard about this phrase, the pale blue dot. Yeah? Anybody wants to tell me how did this come about? I'm not going to throw chocolates. I have nothing on me. So if you give the right answer, you get cheers.
Carl Sagan.
Carl Sagan. And how did it come about?
Voyager's picture.
Yeah, Voyager 1. Voyager 1 in 1977. It was one of the 2 Voyagers that was set out, and when it was almost about 6 million kilometers away from the sun, there we go. It was 6 million kilometers away from the sun, a little close to Neptune, when the ground-based team basically said, turn back and look at our home one last time. So this picture came about from a series of 60 images that was captured, and this was stitched together. And Voyager is known for having done some of these, what they call the family portrait pictures of the Earth. And this is your pale blue dot there. You see that? Equivalent to 1 pixel. And coincidentally, the sun's light was actually shining exactly like that. So this is a very famous image, and this inspired Sagan to give the following title to his book. He called it The Pale Blue Dot, A Vision of Human Future in Space. And back then, what seemed like sci-fi is increasingly becoming reality now. And we have done a lot of missions since then, and we have learned a lot about our space, and also understanding space from a perspective of whether there is life outside of our pale blue dot. And today, the stuff that I'm going to, I need to read this out. Tilina did put up the whole abstract that I sent him, because in the last sentence, I say that I hope we leave with a renewed understanding of the home we might ever know in our lifetimes. So I like what he says here. He says, look again at the dot. That's here. That's home. That's us. And we do not know of one other place out there, either in our solar system or outside of it, which remotely resembles our planet and our home. But hopefully, I don't know, maybe within the next half a century, we might discover places that might look a little like home. We'll see. So, this field of astrobiology, basically it's an area of science that deals with understanding the origin, the evolution, and the distribution of life in the universe. It feeds off of several areas of sciences and math. I didn't put math out here, and I didn't put history and philosophy of science and basically science education, but they're all in there. I'm sorry, I just put a few of them here, but it feeds off of very diverse areas of sciences, and it eventually allows us to think about how the transition from non-life to life would have occurred on the early Earth. Basically, this is just something that Mark Kaufman put out on a NASA site, and it just gives you a flavor of how you can approach this question. One is to study biology that lives at the extremes. Another is to try and understand biology using a completely bottom-up approach, where you literally work with the fundamental ingredients and try and concoct something like life in the lab. And more recently, a lot of inputs are coming in from our understanding of extra solar system bodies and also other planetary systems and moon systems within our own solar system, which is actually telling us more and more about how can we think about the concept of habitability. If you have to think about habitating another entity in our solar system, what are the requirements? Because that is also going to feed into your understanding of what is life and how might we think about it on other systems other than our own planet. But having said that, the story of the emergence of life on our planet is very old. It's a very intriguing story which is still missing a ton of pieces of the puzzle. However, we have learned enough in the last, I would say, 75 to 78 years that we are trying to piece a picture together where several things are coming to view, and I'm hoping that by the end of this talk, I'll be able to share some of that with you. If this moves, yeah. Nothing happens in isolation. The work that happens in my lab is possible only because of a whole bunch of adventurous individuals who work with me, all the way from the graduate level to undergraduate, several undergraduates who have gone through the lab. So I just need to thank them for allowing me to keep this line of questioning alive in a country where astrobiology is hardly known as a science. It is just up and coming. Our lab is by far the coolest place ever because we work on the chemical origins of life. This transition from non-life to life is best appreciated as a transition from chemistry to biology, and I'll soon tell you why that is an obvious way of thinking about this question. Yeah, just a little bit of backdrop. Because we are situated in our solar system, it's good to appreciate when it came about. This is something that most people are in agreement with. About 4.5 billion years ago, the solar system came about, planets formed, so on and so forth. Very soon thereafter, there was a very important event of the moon formation, which happened because of collision of a Mars-sized object with Earth. The Mars-sized object, if I'm not wrong, is called Theia. And that collision essentially led to ejaculation of this little bit of mass, which just then got caught in the new Earth's orbit, and that is how Moon is thought to have formed. Some bits of it are still debated, but for the most part, I think people are in agreement with this. Oopsie, I'm so sorry. Move. Yeah. These two, even though there's no question mark out there, this is something that one of my dear friends who used to be here in LC, his name is Ramon Brasser, him and a bunch of his colleagues are arguing heavily against, but I still will not buy it till I have more solid proof. There's an event called the late heavy bombardment, which is very crucial for understanding how did the original organics come to be on our planet, on our ancient planet. And during this period, just like today, it's of course bombardments, your comets and meteors and meteorites are not bombarding the planet non-stop. But very early on in Earth's history, it's thought that they kept doing this non-stop, and a lot of the important organics which are relevant to life's emergence are thought to have been brought in by this exogenous delivery. And one other thing that is very, very relevant when you're thinking about origins of life is to think about where the important canvas that allowed for life reactions to even be possible in the first place, where did that come up? When did that come about? Where we have a better sense. So this is water. We do not know of any other universal solvent to date that can replace water. If you do not have water, you do not have any of the reactions that keep you and me alive. So water is a very, very, very important ingredient, which is why a lot of the missions that are looking for signatures of habitability or signatures of past life or present life on other extraterrestrial systems or on exoplanets actually look for signatures of water. That is such an important biosignature of life. So how did that come about? Mostly the ice crystals that rode in these meteors and meteorites are thought to have carried all of the water that we see on the planet today. But when did the hydrosphere exactly form is still a little debated, but that's beyond the scope of this talk. But this is sort of a linear scale on which you can see the early history of life on Earth. And what this shows you is that there was extremely interesting chemistry that was happening soon after the Earth formed, 4.2 billion years ago. How did you go from that space of interesting chemistry to what we recognize more as biology today is still unclear, both in terms of the events that would have led to the evolution of this chemical space to a biological space, and also the niches that might have supported it. However, it's very clear that this happened and this is what it is now, but how did you go from this space to this space is what we're going to try and understand today, because that is what is going to tell you how the transition from non-life to life actually came about. Oops, wrong side. Sorry. You remember I told you, I'll tell you soon about why we can think about this transition from chemistry to biology as transition from non-life to life. It's because of this gorgeous continuum that exists between physics, chemistry, and biology. So let's focus on these molecules here. These are what our cells are made of. Some are proteinaceous enzymes, like here it's cytochrome C. It's one of the most ancient enzymes that we know from a lot of phylogenetic studies. This is an enzyme also, but it is made up of a ribose nucleic acid. It's not a protein. It is a nucleic acid, which is a cousin of DNA. And both of these molecules are made up of fundamental monomers. Because of lack of space, I have really only given some sort of examples of molecules, remotely not exhaustive at all, but these are all monomers of proteins called amino acids. But look at them. What are they? You zoom into them. They're actually a bunch of smaller chemical moieties that have been brought together to form these already seemingly complex molecules. And you zoom further into these chemical molecules. What are the chemical molecules made of? They're made up of atoms. So you can appreciate that there's this beautiful continuum that exists between physics, chemistry, and biology, which then allows us to systematically structure questions to better understand how do you go from this space to this space via this monomeric space, which allowed for the emergence of life on the early Earth. So that's how the question gets set. So then the question is, what is life, Sudha? How do you know something is alive when you see it in the first place? You go Google definition of life and you'll see the several thousands of definitions that get thrown at you. It gets very, very confusing very quick because the range is very, very vast, all the way from, ID, intelligent design on one end, to science on the other. So the other way to think about this more systematically is to put together a bunch of people who think about this day and night and work in this space. You remember how astrobiology is an area of science that feeds off of various other sciences. So several of these scientists are looking at different elements of different aspects of things that are important for understanding how to define this concept. So put them all together. Sometime around 1992, NASA Astrobiology Institute exactly did that. Brought a bunch of individuals together. The team was led by a very interesting molecular biologist called Jerry Joyce, and they came up with this definition, which goes as follows. It's a self-sustaining chemical system that is capable of growth, replication, and Darwinian evolution. So if your system in the test tube can actually encompass or have these features of three important features, which is the capacity to self-replicate. All of life is encoded in information, and information propagation is what keeps life going. So you need a molecule which can encode information and be able to replicate. You need a bunch of molecules which probably are in the form of a network that can take ingredients from the outside, cook up, make energy, allow for the system to keep running and throw waste out. That comes from a metabolic network of molecules. And one other super important feature of life, hallmark of life, that we understand from everything that we know today in biology is the fact that life needs a boundary condition. So if you do not have a boundary condition, the chances for interaction between the molecules in that putative prebiotic soup is very abysmal. Because if you have everything happening in an aqueous medium, you're never going to be meeting each other. You're just so far away, you're just never going to run into each other. So a boundary condition is very important. And I'll have a quiz a few slides down the line, which will be exactly in line with this compartmentalization aspect. So, I hope I've convinced you that exogenous delivery via meteorites and comets could have delivered a lot of the important chemicals that would have set the stage for interesting chemistry to come about. We call that chemistry that happened before life. The term we use is prebiotic chemistry, the chemistry that predated biology. But there's another way to think about how interesting molecules in the prebiotic soup, putative prebiotic soup, came about. Terrestrial synthesis, terrestrial synthesis in very interesting niches and settings on the early Earth. The geology was so exciting. There were all these volcanic sort of environments. Volcanoes and the edges of volcanoes are very exciting because you have a niche or an environmental setting where there are a lot of interesting fluxes, chemical fluxes, thermal fluxes, for example, driven by day-night cycles, like diurnal cycles or seasonal changes, or you could be a tidal pool, and tidal activity can cause cycles of dehydration and rehydration. So all of these are very common features that would have been readily present even on the early Earth as they are today. And these two processes are thought to have brought about the fundamental ingredients that eventually led to the primary monomeric molecules that is required for life's the stage for life to emerge was set because of these molecules. Now this is a very famous example of the exogenous delivery business I was talking to you about. This is a meteorite, and this basically fell in Victoria in Australia very long time ago now, in the late 60s. And this meteorite has been one of our first direct evidences for exogenous delivery. So when a bunch of scientists got together and studied this from different parts of the world, they found that this particular rock body basically had all these different ingredients which you actually see in biology today. Amino acids, nucleotides, not exactly the fundamental units of the informational molecules, but even more fundamental smaller pieces of the puzzles of the monomer. They're called purines and pyrimidines. They're basically bases, a whole bunch of things. We can talk about this if anybody is more interested in the chemistry. But this is that piece of rock which first told us, wow, exogenous delivery indeed would have brought on a lot of important organics onto the early Earth. Since then, and this is something that most of you here in Japan should recognize, this is Ryugu, and this was a very successful mission that was led by JAXA, and this is Hayabusa 2 that brought back this sample. And this body which is floating around in the space between the inner and outer planets basically has all the organics that I talked to you, that I said that was present also in the other body that we actually studied after it fell on Earth. This is a much more pristine sample because they brought it back and they used extremely clean sort of approaches to extract the material from it, and it had almost the same suite of molecules, confirming that exogenous delivery is super crucial for bringing in important organics. But I'm going to focus a little bit more on telling you people, how do you go from that bunch of organic molecules, precursor molecules to organic molecules, And once you have the monomeric organic molecules, how do you eventually form something which is the least common denominator of all these living entities that I've shown here? Who are they? You have Mandela, we know T-Rex, we know mushrooms. Anybody recognize this? Giant sequoias from California. This is a giant catfish, a really big catfish. And here is a, it's a bacteria, a unicellular entity. What is the least common denominator of all these living entities? Sorry? Perfect. Man, I don't have a chocolate. Cells. So one way to think about that transition from non-life to life is to think about how do you go from a bunch of molecules to what is the most fundamental unit of all living entities, which is cells. So yeah, first prize. There are a whole bunch of steps that you can think of along the way, and I do not want to focus too much on this, but you basically first ask, where did the monomers come about? Once the monomers came about, how did they form polymers? This is an important thing I want to dwell upon for 30 seconds. If you zoom into your cells, if you zoom into all that happens in biology, all of it is facilitated by what you call polymers. Of course, some of the simpler monomeric entities are doing a lot of important things, but look at the 4 important biomolecular classes of life. What are they? Students?
DNA,
Nucleic acids, more broadly. Proteins.
energy,
Carbohydrates. Those are metabolic network molecules which are more simpler. But if you look at the polymeric entities, one encodes information, which is nucleic acid, one catalyzes the information, one processes the information and forms molecules that can catalyze all of the metabolism in our cells, which are proteins. Then you have carbohydrates, much more evolved function, so we don't have to talk about it. But the fourth one is the fourth important biomolecule.
lipids.
Lipids. And the interesting thing to remember here is 3 of the molecular polymer classes are a product of a reaction called condensation. So if you have to make a polymer, a string of pearl, it's like, imagine a pearl chain. If you want to string a bunch of pearls together, the thread essentially results from a chemical reaction called condensation, where you kick a water molecule out. So in 3 of these polymeric classes, you have condensation reactions which form the polymers. Lipid alone behaves differently. Lipid has a water-loving group and a water-hating group. So the second you put a bunch of these molecules in water, all the water-hating groups will come together and the water-loving groups will stick out. This process results in a very important phenomenon called self-assembly, which allows lipids to naturally form cell-like structures. So one example of lipids, which you don't think about much at all, is soap. Your soap is essentially made up of a class of molecules called? Sorry?
Is it micelles?
Micelles are one of the higher order aggregates that forms, but essentially these things are molecules like, same, just a lipid kind of molecules. Sodium dodecyl sulfate, these are all called detergents. The word detergents actually comes from a scientific term, which essentially belongs, immediately tells you that this is a class of molecules where they have a water-loving group and a water-hating group, but they organically form cells, which is amazing. This particular thing is a micelle, but it's a wrong way of indicating a micelle, so let's not get into the semantics, but it is one of these higher order structure business. So we can now say that very early on, you probably had very, very, very simple cells. We call them protocells, or the first cells, primordial cells, where you had a boundary condition, and this is the boundary condition I was referring to. In all of life that we understand as living today, the boundary is made of a bilayer lipid membrane. So when we think of concocting the first cells in the lab, we start with a bunch of molecules, including the monomers of the compartment, to essentially form these protocellular entities. And it's thought that these molecules, these set of entities, eventually led to what we appreciate as life today. So this is called extant biology, biology as you know today and appreciate today. These are a class of bacteria called cyanobacteria, and these are the firstborn living entities on our planet that we recognize as actually living. These are minimal living systems, which is what we try and understand in the lab. How did they come about? Can you even, I don't mean to play God, but all I want to do is what I cannot, Feynman said it, right? What I cannot make, I cannot understand. Who said that? I forget. I think it was Richard Feynman. If it was not, it's another famous physicist. Sorry about that. What I cannot make, I cannot understand. So what we try and do is we try and make some of these systems in the lab to better understand if they can emulate life-like processes like growth, replication, so on and so forth. So this is a very, very simple cartoon of the tree of life. Tree of life basically is taking every living thing on the planet and putting them on a tree and clubbing them based on some of the features that they have. And based on that, we know that there are 3 domains of life. One is bacteria, one is archaea, and this is us, eukaryotes. And if you trace the lineages back, the original hypothesis was there was a last universal common ancestor from which all the 3 domains of life came about. And that is what held water for the longest time. Till in the last couple of decades, we have started understanding more and more about life and primordial life, that now the tree is slightly more revised. It's very complicated. There's a lot of crosstalk between all the domains of life. Basically, eukarya, which is what we are thought to have formed by an interaction between these two. An archaea gobbled up a bacteria and resulted in a eukarya. But that's beyond the scope of this talk. I want to bring your attention to the base of the tree now. The base of the tree now no longer says Luca. It doesn't say the last universal common ancestor, because increasingly it's thought that those tennis ball-like protocellular entities would have formed communities of interacting cells which underwent some sort of bottlenecks in evolutionary history, which we still do not understand about, which eventually led to the 3 domains of life that we see today. So this is just to give you a flavor of how not complex the most simplest of life today is. This is your bacteria, and you can appreciate the fact that trying to put this together from its fundamental ingredients is completely non-trivial. You give me every single component that this bacteria is made of as individual components, I cannot take all of that, put it in a test tube, voila, I'm not going to get a bacteria. So there's still a lot that we do not understand about how to concoct life fully using a bottom-up approach. So then we try and understand how you can concoct minimalist systems which will still behave like life. And this is us, our cells, which are ultra complex. This is a whole together different ballgame that I don't even want to touch upon right now. But what do these bacteria do? And this brings me to the other approach that we take in the field to understand life and how it came about on our planet. Those single cell entities can do what you and I cannot do. You put me in acid, I will die. You put me in ultra cold conditions, I will die within a few days. You put me in a, very high temperature conditions, above 100 degrees, you will just see me, wither away. But these single cellular entities actually survive all of these extreme conditions. These are called extremophiles. They behave specially, even more specially than regular, living entities. And understanding them allows us to appreciate the limits of life that exist and how these limits of life can actually inform our search for life elsewhere in the solar system or beyond. So both these approaches have their own merits and are very crucial for helping us appreciate how life emerged on the planet and where can it sustain itself. This is a very interesting rock record, and this is for real. I don't know how many of you have been to Western Australia? No. Actually, the Australian family is not here. These are called stromatolites. These probably are not living stromatolites, they're dead. These pillow-like structures are a consequence of biology and geology. And you actually take them and you slice through them, you can actually see these alternate I think I pressed the wrong thing. Okay, no. You see these alternate striations, some are really black and some are golden in color. Essentially, these are cyanobacteria that have gotten encapsulated within these rocks and stay as rock records. So some of these records which have convincingly made us appreciate when life as we understand came about, date back to about 3.85 billion years. When did I say Earth or Earth formed? 4 to 4.2 billion years. Soon thereafter, minimal life just didn't come about, it actually evolved into what we appreciate now as life. So the process was really, really fast. And we still are trying to figure out all the individual steps. But this did something very important. Oops, go back. Yeah. This did something very important to the planet which completely changed the way the planet behaved. Any guesses?
Oxygen.
Yeah, you saw that. So, all of the stuff that I talked to you about, where you go from chemistry to biology, transition from non-life to life, all of those processes are thought to have happened when there was no oxygen on the planet. However, these systems that came about did something super crucial. They didn't participate, I'm sorry. One very important process that kept them alive, that process is called photosynthesis. Yeah, where you use solar energy, you use carbon dioxide and water from the environment, cook, make your food, spit oxygen out. That is the oxygen that is thought to have oxygenated the Earth's atmosphere that we see today. Do you know what the percentage of oxygen in the atmosphere is today?
21.
Correct. Are you a biologist?
Yes.
Oh, okay. 21%. Yeah. Anything more than that can poison us also, yeah? So we need to remember that. Still, the most pronounced gas on our planet is nitrogen, but oxygen is what changed dramatically the way Earth looks like now. And this is us. If you put the history of evolution of life on Earth on a 24-hour clock, and this is not the greatest clock because after midnight you have morning, after morning you have noon, after noon you have afternoon. There's no evening. Anyways, so go with me here, but if you take that clock, if you take the evolution of life on Earth and put it in a clock which is roughly like this, what you'll see is this particular event came about close to afternoon. So our ancestors came about close to afternoon. When did we come about? Very close to midnight, not evening, extremely close to midnight. We've just come here a couple of seconds ago, and what have we done to the planet already? Yeah, so very important to think about what we've been able to do to the planet, which otherwise hasn't happened when we were not around. So this is an artistic rendition of how our planet would have looked very, very early on in its history. And I hope I have given you some flavor of how, despite its inhospitable appearance, there were environments or niches that did allow for the transition from chemistry to biology. But once life came and started evolving really quickly, this is what it did to our planet. It ends up making it look like a pale blue dot, gorgeous looking dot. And this artistic rendition of a terrestrial geothermal system, this is a real geothermal system. This is in the Yellowstone National Park. If I'm not wrong, this is the Great Faithful. And this is a geothermal system which looks absolutely stunningly gorgeous and colorful right now. And where is all of this color coming from? Life, living entities that basically line up all the edges of the rocks here. So this history, I'm hoping that in the last, I don't know, what time is it, Tilina?
We have like 10 minutes.
10 minutes more. I hope I've given you some flavor of this. I'm quickly going to jump to another very important thing, which is to give you a sense that all that we are understanding about these processes within our lab. Oh, is it going to come up, Sudha? Okay, sorry, this is when it all began. These two gentlemen who were in two different parts of the world, one a Russian and one an American with an Indian connection, JBS Haldane and this is Operin. They basically independently came up with this hypothesis, which is now called the Operin-Haldane theory, which posited that if you had the right ingredients in the atmosphere, and they assumed that early atmosphere was extremely reducing, which meant there was a lot of electrons in the atmosphere for fun reactions to happen, and if you had interesting energy sources like UV radiation and other kinds of ultraviolet radiation from the sun, thunder, lightning, all of that stuff, you could actually go from a bunch of inorganic molecules to what we appreciate as organic molecules today. But a theory is a theory is a theory till it is demonstrated with an experiment. And this came in The year? Any guesses?
1951.
You're close.
Two.
The same year as the DNA structure was described. 53. 1953 had a whole bunch of milestones, scientific milestones happen, and this is a very important milestone where Stanley Miller joined Harold Urey as a postdoc, if I'm not wrong, or an early career researcher, and he said, I want to try and demonstrate operant Haldane theory in the lab. So he went ahead, concocted this setup. He actually heard Urey give a talk about this in University of Chicago, if I'm not wrong. Anyways, he went and said, yes, this is my dream experiment. Can I try and do it with you? And they said yes. And they got together, two of them got together, and Stanley did all of the, work that typically a grad student would do in the lab, the ass load of work, put the whole thing together and went ahead and showed that you can indeed go from a bunch of inorganic molecules to what we recognize as organic molecules, which are the fundamental building blocks of proteins. And you had a whole suite of molecules. I'm not talking about them, but I'm happy to talk about it separately. And where do we think these interesting transition processes would have happened on our planet? I hope I gave you some flavor of the terrestrial geothermal environments, which we think were rife with very interesting thermal and chemical fluxes. Here is another very interesting volcanic environment, but it's not on terra firma. It is terra subfirma, way deep down in the ocean. I don't think that's the real term, I just looked at it. This is the floor of an ocean, and again, defined by volcanic activity, which essentially means a lot of very interesting rock-water interactions happening at high temperatures, and there's a thermal gradient, and the chemistry that allows for a chemical gradient, and depending on whom you talk to in the field, they'll either say life emerged there or here, and I belong to this school for reasons I'm not going to get into now. I think very interesting chemistry is plausible there, but I can't wrap my head around certain other problems that scenario could pose. So, we think this is where life emerged in terrestrial geothermal pools. And I'm not going to talk about this, but happy to talk about it later after I'm done with the talk. So, we are very interested in understanding in the field and in our lab, how do you go from a bunch of fundamental monomeric entities in the prebiotic soup to what looks like minimal living entities, because without understanding how the step came about, we will never know how life can come about from a bunch of interacting chemical molecules. And I'm happy to state that the puzzle is, coming to view now, and we are understanding how you can indeed go from a bunch of inorganic ingredients to precursors that would have led to the formation of proteins, to the formation of nucleic acids, to the formation of the lipid bilayers. But like I said, a lot still needs to be understood. We not only, this is something that is true for people in LC2, we not only do research in the lab, we also go out into the field to what is called analog environments. These are environments that are reminiscent of a planetary system or a body, and we actually try and understand if what we understand in the lab actually holds water in realistic conditions, because realistic conditions are way more complex and diverse. I'm going to jump quickly now. Everybody knows this, no? Yeah? This is the Perseverance rover, which is currently on Mars, doing extremely cool and important research, which hopefully in the next decade will tell us a lot more about whether Mars could have at some point had life in its subterranean environments, but it's still very tricky. This was a technology demonstration, not going to talk about it, but a very cool helicopter flying around. But the best we can do is to draw up a story that is consistent with all the evidence that we can get from what geochemistry tells us, what minimal biology tells us, what extreme life can tell us, and you can put all of this together and try and understand this puzzle. And why is this puzzle very important, other than the fact that, at some point, that probably is me, and hopefully it will happen in my lifetime. But it's important for understanding whether there is life elsewhere in the universe. Do I have 3 more minutes? Yeah. How can you think about that? You can think about, like I said, whatever you understand from what we see on our planet. For this, you need to know that there's a very important concept called the habitable zone, which is essentially finding a planet, or a body that is just at the right distance from its star. Because at that just right distance, or the Goldilocks zone, that is where the body can hold water. And you remember how I told water is fundamentally crucial? No water, no life. We do not know of another solvent that can do what water does. So this kind of limits the bodies that you can look at where life could potentially arise or could have been present. And in this just right planets, we try and look for, signatures of life. And what kind of signatures can you look for? You can look for something called biosignatures. It could be a whole bunch of things, a substance, a structure, a pattern, or a process that essentially, or an ensemble of all these features that indicates whether there was current or formal life on the planet. And like I told you, it completely changes the way a planet appears over time. Yeah? It leads to large-scale modification of the atmosphere, the surface, and its appearance. So when we look at something that we do not know of, we will never know whether it looked the way it looks several millions or billions of years ago. But some things we understand about several signatures that emit from the surface of the planet are indicator of life processes, and that we can look for. And I'm again not going to talk about what these detailed signatures are, but you can look for them in the UV spectrum, in the IR spectrum. You can look at it in various wavelengths. And you can use a whole suite of techniques that allow you to detect molecules all the way from angstroms to processes in the range of kilometers. And this is just giving you a flavor of what all you can identify that might be indicative of life on another system. And we are now trying to understand, and this is within our solar system, space agencies across the world are actually, particularly with NASA taking the lead on this, is trying to understand other habitable worlds and if they could potentially harbor life. And some of the examples, Mars we already touched upon. Perseverance is right now out there, and there's been a whole bunch of previous missions that went out there, and several space agencies still interested in understanding processes on Mars and trying to send rovers, and it's going to keep going on. We know how to get to Mars, and it's the easy part. The more difficult part is to get to these systems, Europa and Enceladus. Europa is, if I'm not wrong, Jupiter's moon. Titan is moon of Jupiter, I'm sorry. Europa and Enceladus are very interesting. They are called icy worlds, and beneath their uppermost surface, they have very interesting, it's thought that they have vast bodies of water. And in Enceladus, there's another very cool thing happening. It's shooting off plumes every now and then, and that could be possible only if there are hydrothermal vent systems in the bottom, which is very, very indicative of maybe this particular body has niches or environments where the transition from non-life to life could have been facilitated. So maybe there is life out there. So I think I will finish with this because I don't have too much else to say. These are just analog environments to give you a flavor of the kind of, this is actually Mars, and these are alluvial fans which you can find in high altitude desert regions on Earth. This is from a very important Mars analog which is in India, the northernmost tip called Ladakh. It's a Union territory, and that's one of our field sites. Not that particular location, but we do work in Ladakh. This is a hot spring which is thought to be the primary niche in which the interesting reactions are thought to have happened. And happy to share that a whole bunch of missions, both in the past and present and in the future, have a lot of instruments on them that are asking precisely astrobiology questions. In the past, though, if you talk to hardcore space folks, they'll say that it was all doing planetary science, not astrobiology, but it still was asking some questions whose answers had fundamental implications for understanding how life emerged, evolved, or is sustained elsewhere in the universe. But we have a whole bunch of very interesting missions. This is called the Habitable Worlds. What does the O stand for? Observatory. Yeah. So this is HW, which is about to happen, or is it already happened?
Just a concept.
It's a concept now, right? But
In the
it'll happen.
2040s, I think.
Say that again?
2040s, I think.
Okay, we're not too far. But this is very much there, no? That's JWST. And there are people in the room here who actually use data from JWST to understand some very important questions regarding planetary systems and aspects pertaining to it. But yeah, I'll thank you for your attention, and I'm happy to take questions.
Thank you so much. So that's lost lot to sort of grasp in a few milliseconds of our clock.
Microseconds,
Yeah.
picoseconds.
Questions? Raise your hands if you have questions. Let's start from this side.
Hey,
Hi. I don't know if this is conference style, but I'm Ellen from Elsie. This is a great talk. Thank you so much. It's so related to my work, so I'm just going to nerd out for a second. But you really talked heavily about the transitory nature of Earth's climate as it moves from Archean to present-day Earth. And I'm thinking, when we think about or are looking for biosignatures on other planets like Mars, we know that Mars wasn't always what it is now. How do you suppose that we address some of the concerns about how biosignatures may hold up over time through this sort of transitory nature as you go from maybe habitable at one point to now uninhabitable, or in other exoplanet solar systems, we don't know what that sort of transitory nature seems like. It's just not up in our capacity to observe it. So what are your thoughts about that? I would love to hear.
thank you for asking the question. This raises a much more important concern about even classifying something as a biosignature, because you're wearing sort of blinders when you're now cataloging biosignatures, because you appreciate it from this perspective of what life we have on Earth now and what are the fundamental signatures that it embodies, right? Having said that, I think very little work has gone into understanding. There is some work in the space. What happens to these signatures over time? What happens to them under different conditions, environmental conditions? So what else should we be looking for? What is severely lacking, and that's where our work plays a very important role. We look at what are called abiosignatures or prebiotic signatures. We want to call it prebiosignatures. And these are not even officially acknowledged as putative signs that we are supposed to be looking for, because maybe a system, a planetary system, or within our solar system, or a moon or any exoplanet is on the way to hosting life, but it's still not there in terms of having your proteins, your nucleic acids, or the kind of signatures that might come from having these very complex biomolecules. What we are arguing for is you need to factor in a whole bunch of other kinds of signatures that could tell you more about whether the system is in a position to host life, potentially, one. Two, if you're looking at Mars, which now looks extremely inhospitable and looks dead, essentially, what would you look for if it did have life at some point? I think it's super crucial for us to be doing a whole bunch of studies where we're trying to understand how they degrade over. Temporal we cannot do. We cannot live for billions of years and follow through with these experiments. However, you can simulate other physico-chemical parameters, very high temperatures or extremely low temperatures, and try and systematically, at least for the 4 major classes of biomolecules, try and systematically understand what happens to these signatures over these processes, during these processes, and at least have a catalog of them that we can look for. As of now, signs of oxygen, ozone, water, methane, in the biological space, nucleic acids, and some other simpler versions of these oligonucleotides or peptides. These are all classified as a whole bunch of signatures, and there's a whole bunch more. But yeah, it is not an exhaustive list at all, and we really need to start thinking more about what else could encapsulate this list, and what else should these machines be looking for when they go out to these worlds to look for signatures. I hope that answered your question a little bit.
It does. Thank you.
Let's go here.
Thank you very much for a very fascinating talk.
I'm not related. I'm more social science.
Ah, nice.
However, all the environmental studies also relate to your topic, I think, very strongly. My question is about the water. When you talk about the water, it's more molecular structure, I think, maybe, because I want to know how fresh water that we need to survive, but most of our surface of our planet is covered with the salty water, right? We might use to some extent, but it doesn't provide for every type of organism and the necessary conditions. So how much does this matter?
Oh, it matters a lot. You've touched upon another very important ingredient of life which I didn't talk to you folks about. These are basically metal ions. And your salt water is full of these metal ions. For example, if you're looking at seawater, which is very, very salty, you can have sodium there on the orders of a couple of hundreds of millimolar. It's a lot of concentration of sodium ions in one place. But having said that, you also alluded to this somehow indirectly in your statement. There's still life there. Even today, there are organisms that are specially suited to populate that niche. However, to go back to your question, when I say water being fundamentally crucial to life, it's not water in isolation. Water was constantly having this crosstalk with a whole bunch of rocks. And the second you're looking at niches where you have these rock-water interactions, you're going to have a whole suite of sodium-like monovalent and other divalent ions which are present in that milieu, which is where my analog research, alluding to analog research, is a very important thing, because in the lab, what we end up doing is I have my favorite reactions or sets of reactions, and I take a very minimalistic reductionist approach to hash it out to death and understand how it works. But once you've understood, once you've had that preliminary understanding, you take that same reaction and say, I'm going to now shoot myself in the foot and go and study this in that external environment where you have no control on the parameters. The water temperature is crazy because a lot of these high altitude desert springs are at high temperatures. They are not at ambient temperatures like our bodies are at 37 degrees centigrade, 50 degrees plus. And it's thought that when Earth was hosting this transition, Earth was very, very hot. And depending on whom you talk to, it's all the way from Darwin's warm little pond, 60 degrees C to 100 degrees C. So when we do many of these favorite experiments of ours to understand these transition reactions, one very important thing that we should be doing more systematically is to try and understand these processes under varying temperatures, under varying pH. pH is basically your acetic acid vinegar is very acidic. Your alkaline seltzer, whatever you call that, it's very basic. So you have a whole bunch of environments in which you have a lot of protons or very little protons, and that seems to affect processes very differently. And ions, one of the most important metal ion which is allowing you and me to have this conversation today, can you tell me what it is? If that metal ion doesn't exist, we are dead. Oh, come on, somebody should tell me this.
Iron.
Iron, correct. What does iron do? It sits at the core of your hemoglobin monomer and it binds oxygen out here and it releases at the level of your tissues. You don't have that iron at the core of the molecule, you're dead. This function of oxygen breathing and releasing doesn't happen. So we know that a whole bunch of metal ions still are being used in biology. But exactly why some of that got selected, because if you know, how many of you have heard the term periodic table? I'm not going to get into it, but the table has a whole bunch of elements, and along with iron you have a bunch of siblings who behave very similarly because they have the same number of protons and neutrons. But why did iron get selected for this job and not something else? We don't know. But to go back to your question, water was not the canvas in isolation. It's one way to think about it is that it's not that beautiful silky canvas. It's a canvas which had a lot of natural, follies in it and natural, ups and downs in it, all of which was very, very necessary for a lot of processes to happen. So yeah, fresh water great for drinking now, but I can't use it for my experiments. Useless. It won't work.
Yeah, that's a good.
Ha.
Chemistry is really complicated and biology is really complicated. So if you go back to that definition of life, how important is it that the word chemical is there? And are we just sort of being, not carbon fascist, but basically saying this is the type of life we like? And are there examples of life without the chemical in there?
That we see now?
Yeah.
Yeah, no, we don't actually. So
Okay.
here's the thing. It's okay for us to be carbon fascists. There's a reason why we should be carbon fascists. The closest cousin to carbon is silicon.
Yeah, yeah.
But all you can get silicon to do, the second you throw oxygen at it, is to form sand.
Sure. So, but if we get rid of chemistry completely, and then
How else can you think about
we're looking
it?
for networks that have got some boundary conditions and have some self-organized Darwinian pressure on them, right? That's what we're looking for. There are some candidates, right?
Can you give me one example?
Yeah, it's in the title of your talk today, narrative. If you look at narratives out in the wild, that's my research field. You see self-organization.
Yes, you do. However, if you want to understand how the biochemistry
Yeah, I
that
don't necessarily want to understand that.
that is why I have to invoke chemistry. Otherwise, I don't have to invoke chemistry.
Yeah, that's right. But are we seeing? If that's the definition of life, then are we seeing life in unexpected places, in different forms, right?
As of now, the answer is we do not know and we don't see them. Is it because we are wearing the blinders that we're wearing, and hence we're missing it out? I don't know. But like I said, it alludes a little bit to the answer I gave to Ellen's question. I got your name right, no? Okay. Is, for example, the nucleic acid that I was talking about, which I said is an information coder. I can tell you that I work on molecules that exactly look like DNA and RNA, but are not DNA and RNA. They do information coding too. So when I'm looking for life elsewhere, am I supposed to also be looking at all of those other alternate chemistries?
Yeah, well, you just look at the information coding, right?
That's it. But how to think about it in minimalistic terms is completely non-trivial. Because I think the biggest problem is appreciating the planetary history of a body, a geological history of a planetary body or a moon or a exoplanet. Knowing the one planet that we know so well, we have such giant loopholes and lacunae in our appreciation of its geology that we still make up some of the things as we go. So then how do we even remotely start understanding systems which are away from us, and all we can appreciate is all the signatures that we can read from them using all these telescopes, and we still do a shoddy job of our own planetary history. So how are we going to really be able to appreciate every nuanced detail that can then allow us to better come up with some of these contingent alternate chemistries or processes? I don't know, it's a very difficult.
Yeah, chemistry is too complicated.
Yeah.
Biology is complicated.
Biology is even more
Yeah,
complicated.
it's way too complicated. We don't understand why.
Yeah.
Let's go here.
Okay, so thank you for your talk today. It's very interesting. I guess my fascinations about this presentations is more about the scaling up of the biomolecules. I guess the formations of the biomolecules from the inorganic molecules itself is, at least for me, it's not very unique. You know, if you put carbon dioxide and you put hydrogens together, you know, one way or another you'll get an ethanol or I don't know, methanol or
Oh, you can't.
or methane. But the scaling up of the biomolecules itself to form an RNA, for example, or a lipid bilayer, for example, that's I think you didn't include in today's presentation. So do you have any like?
I will use one
short
example
conclusion?
of scaling business, right? So if you take the cells that our bodies are made up of today, and if you look at the boundary condition, which is a bilayer, a lipid bilayer, the fundamental monomer is essentially a molecule called a phospholipid. So it has a phosphate head group and it has 2 hydrocarbon chains, and it can self-assemble like crazy under a diverse set of conditions. So what we're probably seeing now is a process of molecular evolution that selected for these molecules And along the way, you know, a lot of processes, cellular processes, started coding for their formation and so on and so forth. But when I'm talking about the protocellular entities, I'm talking about a much more simpler boundary molecule, the bilayer forming molecule, which is essentially one ball as the head and one chain as the tail. These are called monoacyl lipids. And these are thought to have very readily formed under the kind of reaction conditions that you talked about. Take water, take carbon monoxide, but under high pressure conditions they can form hydrocarbons. And then you think about you can invoke some chemistry to embellish its head group. So you now form what is called a fatty acid, which your phospholipid is still made of, but that in isolation, under certain unique set of conditions, can self-assemble into a bilayer. And when I'm talking about a protocellular entity, I'm only thinking about a lipid landscape which is much more simpler and which would have come about much more readily under early earth conditions. So same for nucleic acids, and that's the example that goes back to what I mentioned to his question. There's no reason to believe that the biochemistry that you're seeing now in the informational space is what might have been very early on. Because in the lab, I can invoke alternate chemistries which are much more readily, which are amenable to more ready emergence from the prebiotic soup than your RNA is. RNA is a rock star molecule because it does what both DNA and proteins do, but to make an RNA polymer from its monomeric entities is a pain in the wrong place. It's a very tricky molecule, a very sensitive molecule. But the second I keep some of the fundamental, what is the word I'm looking for? So when you make the string of pearls, the chain has a certain chemical nature. If I disregard what the exact structure is now and can come up with another moiety that can still behave in a similar manner and provide the molecule with the same kind of negative charge, I can now start invoking chemistries that you don't see in modern biology, but can result in a polymer which will still encode information. But why do we not see that in biology today? So there is a whole process of chemical evolution, and I'm happy to share these resources via Telina. There are some really cool short videos, 10 to 15 minute videos by this guy called John Perry. I was trying to remember his name this morning. John Perry, he got funding from NASA, and he has these bunch of videos which he does under his handle called Stated Clearly, and he actually talks about some of these very dense concepts with animations, which makes it a little more readily understandable. So today after you heard this talk and you go and you Google John Perry and Stated Clearly and say origins of life or chemical evolution, you'll appreciate some of these things even better, because then he uses lovely animations to talk about this. So hopefully I'm touching upon how you go from still low complexity, but eventually more complex came about, but that got shaped by a lot of environmental conditions which we still do not understand.
That all happened in 0.something billion years.
Yeah, looks like it. That's the argument, that it happened in Hadean. Yeah.
Okay, so we are going to take one last question, but you can talk to Sudha afterwards in person as well.
Yes. My question was about the biosignatures, and especially how to deal with the ambiguity issue. Because if we select, I will take a very simple nitrogen example, high level of free oxygen as a biosignature, how can we be sure it is life or not some other processes? And for example, for the case of oxygen, we had the discovery recently that in deep sea there are some purely abiotic processes
That can result in formation of
black smoker and the seawater that is producing oxygen.
So the one super quick answer to your question is you never look at one biosignature in isolation. You are always going to look for a suite of them, and unless and until you are able to say, oh, this is there, and this is there, and this is there, and this is there, okay, the chances, the percentage probability of you being able to detect life in that space is very, very low. If you take 4 or 5 things off, then it suddenly starts getting higher and higher. but you're raising an extremely important point of how we shouldn't get blinded and carried away by this one sexy signature or two sexy signatures and say, voila, life is happening there or happened there or is going to happen there. Because, as you very correctly pointed out, a lot of these molecules can also be abiotically generated. The very famous recent example in the last 3-4 years was that of phosphine signature in Venus. And there was this huge hoopla of, yeah, Venus probably has life and blah blah blah. Phosphine can form very readily by volcanic processes too, and other kinds of abiotic chemical processes. So to date, we are not sure if the presence of phosphine on Venus that was detected is actually an indicator of life. However, the upper atmosphere of phosphine is more amenable to chemistries that I'm talking to you about, where it is not as crazy high temperatures as its ground is. The terra firma on Venus is at around 400 degrees C. But in these upper clouds, you have these, what is the word I'm looking for? Bubbles, no, gases. You have this gaseous bubbles or whatever like that. They are a bit acidic. The temperatures are much more amenable, and I can think of some interesting chemistry that could be possible there. So if I'm looking for life, I should actually be able to somehow trap these Venetian gases and bring it back in pristine conditions and look at them in the clean room and try and understand if you can actually see life there. That would be what I'd do. So to go back, suite of biosignatures, get excited. One biosignature, please be extremely worried because it could be a product of abiotic synthesis.
Okay.
Great. Thank you so much, Sudha, for this amazing talk.